And so today is the this will be the last session, and there will be two speakers, and after that we'll give vote of thanks. So first speaker is Professor Rajaram Nityananda. He is a senior professor at the National Center for Astrophysics, Pune, where he was also the director till February 2010. His broad research interests are optics, image processing, gravitational dynamics, and condensed matter physics. He is currently the associate editor of the Journal of Astrophysics and Astronomy, published by Indian Academy of Sciences. So he will be talking about Chandrasekhar's contribution to radiative transfer and appreciation.
Thank you, Kalyan. Let me clarify what this appreciation is. It's certainly not that I'm giving a certificate to Chandrasekhar. The background is that some 15 years ago when he passed away, Math Science, the same friendly audience, gave me an opportunity to give a kind of broad survey of his work, which I called the 6 Faces of Subramaniam Chandrasekhar, based on 6 books. I noticed that Freeman Dyson in Recent Physics Today counts 8, but this is one area where I would claim superiority to Freeman Dyson, because we all know that Subramaniam is synonymous with Shanmugam, which is 6 faces. So anyway, but the point was that I realized even at that time that I didn't appreciate the radiative transfer enough, and when this opportunity came along, I went back to the book. So the spirit is somewhat of Chandrasekhar's own venture of reading Newton's Principia and trying to figure out how the great man thought, and that's what I have tried to do in this exercise. So that's the spirit of this talk. So while you're looking at the plan that I have, let me just give a broad overview of radiative transfer. It is one of the absolutely bread and butter topics of astrophysics, the kind of practical thing that Ramesh told you about. It could concern a very exotic object, but very practical issues of how the radiation which we observe, which carries all the information that we will have, gets shaped by events of emission, absorption, and scattering. Okay? And the proper accountancy of all these in various different astrophysical contexts goes by the name of radiative transfer. Right? And it's a somewhat mundane subject. If you think of gravitational collapse, general relativity, perhaps even magnetic fields, the kind of things that Chandrasekhar worked in, I would say it's a somewhat mundane subject, and that added to my sense of being intrigued. What attracted him to this, and why did he describe this as the happiest period of his scientific life, more than once? So, if people will forgive some elementary stuff to start with, absorption can be simply described by a fractional decrease in intensity, which is proportional to the distance. Constant of proportionality alpha is some kind of absorption coefficient. The product is dimensionless, and it's invariably denoted by tau. Well, in this case d tau, because it's an infinitesimal change in the logarithm of the intensity. And precisely because it's of that, you can integrate it, and as the radiation goes through this slab, under simple absorption, the incoming radiation gets attenuated by the exponential of minus this tau, which is the okay. So that's simple absorption. Now let's add emission. So the previous equation now gets another term proportional to the distance traveled along this ray, which has an emission coefficient, epsilon. So you have this di dl is minus alpha I, which we had before, and plus epsilon, the emission term. Doesn't need a Chandrasekhar to solve this equation. So, so this is the solution, which is written below, has 2 terms, as we have all been taught, when you get dy by dx equals py plus q. So the first term is what we've seen before, the incoming intensity attenuated by this tau, evaluated, the integral of the absorption coefficient evaluated through the slab. And the second is the emission at different layers, which then emerges attenuated by tau between that layer and the output. Okay? So the 2 terms are represented by the 2 arrows. And this tau is called optical depth. It's a somewhat opaque term, but astrophysicists use it, and we will use it as well. It's dimensionless, And in a sense, it is the relevant parameter if you want to know how much the radiation has interacted with matter. Okay? You can think of it as a dimensionless number, the number of mean free paths. That's one way of thinking about it. Okay? And maybe if one wanted to increase sales, you could call it the tau of astrophysics. Okay. So here is a simple illustration which is relevant to our story a little bit. So if you look at the sun, and you look at the center of the sun, your line of sight starts penetrating, and as the previous equation shows, most of the epsilon which you see will be where tau is of the order of 1 or less, because the rest will be highly attenuated. So, I mean, when we say we see the surface of the sun, that's not an exact statement. It depends on the direction of the ray, it depends on the wavelength. Okay? So when you reach this tau equals 1 surface, it's what we call the photosphere. And you can see that when you go to the edge, you may have to travel to reach tau equal to 1. You will reach it over some distance, but that point will actually be higher up. And it is an observational fact that as you look toward the edge of the sun, it's darker. It's called limb darkening. And the relevance to reading Chandrasekhar's book is that in some problem, when he solves for the emerging radiation, and he solves for the law according to which the intensity of that radiation falls off as you go from the normal out at some angle, he calls it the law of darkening, which again might be a little obscure for people who don't do astrophysics, but this is the phenomenon to which it refers. And in fact, a lot of the mathematical effort that he put in goes to determining this law of darkening. So let me make a comment here. You heard of the canonical radiation law, the blackbody law, and there it turns out that this intensity actually doesn't depend on angle. You have uniform intensity emerging into a hemisphere, okay? But that's only in the case of a black body, and it's non-trivial to calculate this, and it also carries some interesting information, okay? So all this belongs to the area of stellar atmospheres, and which is one of the pillars of astrophysics. So if you think of it from the point of view of the equation you just saw, if you know alpha and epsilon as a function of x, that's the end of it along any given ray. And there are different situations you can encounter. The simplest is what is called local thermodynamic equilibrium, where the population, level populations which determine absorption and emission are entirely controlled by local temperature and collisions. So you really know these things as a function of height, okay? And okay, interestingly, a lot of the data for doing these calculations comes from some tables made in Los Alamos for obvious reasons. They also dealt with radiative transfer and other situations, okay? Now, and of course, stellar spectra have given us enormous information. And of course, Chandrasekhar knew this. So even before he worked in the area, the fact that this was very important in astrophysics. Now, specifically, the kind of areas where he made a contribution and where I will be trying to bring out some of the nice things he did concern very hot stars and concern situations where it's not just emission and absorption that we've seen up to now, but also scattering. And scattering does two things. Number one, if you just scatter photons of, say, hot electrons, because the material is completely ionized, then it's not quite a blackbody situation, because you can't change the number of photons, at least by simple Compton scattering or Thomson scattering, okay? So that's number one. And you also have to do things self-consistently. If you don't have a locally defined radiation temperature, and that is what is called non-LTE. And in particular, this happens not in stars like the sun, but hotter stars. In hotter stars, the radiation which you see emerges from a photosphere, which is really an electron scattering region. Incidentally, it also happens for the universe. I mean, the cosmic microwave background which we see comes from a scattering surface, not an emission or absorption surface, okay? So that is the broad context of Chandrasekhar's work on radiative transfer with emission and absorption, of course, but his definitive contributions were precisely in those situations where scattering was important. And I want to say a little bit about what scattering does to the problem, why it makes it more interesting, more subtle. But the kind of situations you have, I've told you about the hot stars. Interestingly, we are talking of the 1940s, and Chandrasekhar was certainly aware that in the same University of Chicago and some other part, people were worrying about neutrons bouncing around inside blocks of graphite. And it turns out that the kind of equations which govern the distribution of these neutrons with angle and with depth are very similar. There is, I think, only one allusion to that in his book or in his papers, where, where he uses this interesting word. The reader will note, of course, that this is also applicable to the situation of neutrons in a pile. Okay, that's what they called reactors in those days. Okay. So just to introduce scattering from first a physical point of view, I'd like to say that, like charity, it begins at home. So all of you have admired the colors of monsoon clouds, and poets have waxed eloquent about them. But until I got a little educated, I didn't realize that the dark clouds are not a different kind of cloud, you know, even though they were given different names. It's just that they happen to be clouds where the radiation intensity at the bottom is small. It's been attenuated by scattering. Okay. Now, the attenuation by scattering is not quite the same thing as attenuation by absorption, and actually that's a good thing, because if you think about it, as clouds cover up the sun, pretty soon you don't see the image of the sun at all. You know, so direct rays from the sun are exponentially suppressed. So if this tau was say 4, then what comes out is just 1 by 64, right? Which is very e raised to minus 4 is roughly 1 by 64, just a few %. But it is actually our experience that even on cloud-covered days, you know, we don't freeze. The solar heaters do give you something. So the fact of the matter is that even though the direct rays from the sun, which have not been scattered, are exponentially attenuated, there are still many other rays which manage to reach the bottom of the cloud. So exponential minus tau is what you get if there was true absorption, if you have a slab of optical thickness tau. But if the tau is entirely due to scattering, the law is quite interesting. It's 1 over tau plus a constant. Okay? So the attenuation is much weaker. So in the example I gave you of optical depth 4, it would be something like, you know, 1 by 4 or 1 by 5, which is closer to the truth. Okay? I mean, don't take the 1 seriously, but that's. So I'd like to bring out the mathematical features of radiative transfer with scattering, and that is best done to isolate just that problem by separating. So forget about emission and absorption for the moment. I mean, you have a source somewhere, either deep inside the slab, so that is the transmission problem, or a source in front of the slab, so the radiation falls on the slab, bounces around, and comes out. Okay? And the latter case is what happens when the sun illuminates planetary atmospheres, and the former case where the photons generated by deep inside the star fight their way out. Okay? So now I'm going to put down a one-dimensional model which brings out the features of radiative transfer with scattering, and it has the advantage that it's easily sorted out. So now because it's one dimension, there are only 2 directions. The radiation can either travel to the right or to the left, and if you call the relative intensities R and L, so this equation tells you that on the one hand there is removal from the R beam by scattering, okay, and that scattered radiation reappears equally in both the R and L beams. Okay, so that is what the first equation describes, right? A simple scattering, and it's conservative. The same amount of radiation reappears. Now the second equation could be obtained from the first simply by interchanging R and L, except for this small thing that we have fixed the direction of x, and we are not going to change that for the second equation, right? So whereas x is in the direction of propagation here, it's in the opposite direction here. That's the reason for this extra minus sign, but otherwise it's exactly the same equation, right? So then you add these 2 equations, and you find that R minus L is some f, and the rate of change of R minus L is actually 0. I mean, everything cancels. Okay? So f is the flux, and this tells you that you get df dx is 0, the divergence of this flux is 0, which we could have probably said right from the beginning, because where can this is a steady state, so you are not going to accumulate photons, and the divergence is 0 because there's nowhere for the radiation to go, it's conserved. Okay, so that's what this expresses. But if you add the 2 equations, I mean, if you subtract them, then you get R plus L, which is the energy density, and that varies with tau as minus the flux. You can just do that. which again is a sort of familiar equation. It looks like a kind of heat conduction equation, that the flux is minus the gradient of the energy density. So this is the sort of simple forward-backward discretization of the radiative transfer problem with scattering. It was done by Schuster and Schwarzschild in the early years of the 20th century. And of course, Chandrasekhar pays due homage to these pioneers. But clearly, more things had to happen to be more quantitative. So by the way, this is where that 1 over tau law comes out from, if you were curious. So now we know that the energy density decreases linearly as you go through the slab, but the difference between R and L remains constant. So for example, you have 5 coming in here, but the difference is 1, and that difference is preserved until you hit a place where L is 0, which is the other end of the slab, where there's nothing coming in, but so you have 1 coming out. So here, in this case, you have 1 over 5, and in general, you will have 1 over 1 plus tau. Okay? And as far as physics is concerned, this is actually a useful thing. When one teaches, as I have done, joint astronomy program students, you do something simple so that they appreciate the difference between scattering and this thing. Now, from the mathematical point of view, what this actually does, now let's go back to 3 dimensions, is that epsilon term is still there, but now the different rays, the different directions get coupled. So I want to contrast this to the case of LTE, where epsilon was sort of God-given by the local conditions. But now epsilon is obtained from the same I living at that point. You have something going in some direction. By the way, it's a long-standing tradition in this field that you denote the cosine of some angle by mu. Okay? So this equation really says that something going in a direction mu prime gets scattered to mu, and that acts like emission in the direction mu. So now that those simple equations, those Bernoulli type equations, get coupled. Okay? And that is what makes the problem interesting and subtle and worthy of many people, not just Chandrasekhar. Okay? So now to again bring out the basic things and not to get bogged down in details, let's look at the case of isotropic scattering. So that sigma mu mu prime will actually just be a constant. Okay? So this is the radiative transfer equation with isotropic scattering. So let's see how it differs from the forward-backward. In the forward-backward, we had mu equal to either 1 or minus 1. So that's why you had either dr d tau or minus dl d tau. But now you have, so the path length, if you have so now the meaning of tau is slightly changed. Earlier it was tau measured along the ray. But now tau is actually, you have this parallel slab, you have a situation of axial symmetry around the normal to the slab, and tau is just the depth measured normal to the slab. So the actual optical depth is d tau over mu. If you propagate in a direction theta, you traverse a longer distance. Okay? So that's one point. This is the absorption term, and this is the emission term. Okay? So this half is just the average of I, so being restored. So it's now an integral differential equation, and it's this is our old epsilon term, and but traditionally at this point it's denoted by J. So J is just the energy density. So now you have a situation where I, the intensity, is a function of depth as you go into the slab or as you come out. It's also a function of angle, which is mu. So all those have been suppressed. So I is a function of that. And it's integral differential because you have the integral of I here. And this J is of course a function of only depth because you have integrated over. Okay? So what did people do with this equation? Now the practical people, the astrophysicists, of course, as I said, the first people simply discretized it as forward, backward. And then people said, let's take moments. So we've seen this already, J, which is the energy density. If you multiply by cos theta, that will clearly give you the flux. I mean, we saw a baby version of this equation earlier, where it was R minus L, because cos theta was plus or minus 1. This is the general equation. Flux. And then you take more and more moments. Okay? So I times mu square is K, and so on. And therefore, instead of solving for I, you think of I as expanded in spherical harmonics, and you solve for moments. But you see that you will get a set of equations which do not close. So, you know, if you integrate this, you will get a nice equation for, you know, df d tau. That's fine. That you will get the conservation of f. But then if you want to further get an equation for f, you know, you multiply by mu here. So here you will get the flux, but here you will get k. And it keeps going like that. Now, this is where different people have different styles. Now, Eddington was interested in many things, and he said, look, this is, I mean, how different can K be? You can have, deep in the interior, you have radiation going in all directions. So I is a uniform function on the sphere. By the time you come to the surface, let's assume it's uniform in a hemisphere. Maybe it's not quite uniform in the hemisphere. There is some darkening, but never mind. All right. In both cases, interestingly, I times this K is just J by 3 because the average value of mu square is 1/3. So he said, look, it can't differ terribly. So let's just say that K is equal to J by 3, which I liken to Alexander coming and cutting this Gordian knot. And he introduced something called the Eddington approximation. And I have to confess that until I got this deeper interest through Chandrasekhar, I used to teach joint astronomy program students. I would teach them the Eddington approximation, and we would go ahead and get all the useful results. And many people, including Eddington, were quite happy with this. Okay? But clearly, I mean, this is not a solution to the mathematical problem. And it attracted the attention of some pretty powerful people. So here is Wiener, whom we've all heard of, and Hopf, whom everyone in math science has heard of, except that different parts of math science have heard of a different Hopf. So the topologists, of course, know about one of the Hopfs, who had the Hopf map and the Hopf fibration. And the dynamical systems people know about the Hopf bifurcation. So it's that one who teamed up with Wiener, and he went back to this equation. He said, okay, here is J. Okay. Now take a formal solution. Imagine that you knew J. So J is a function of tau. Energy density is a function of depth. So take a slab at tau prime, and how does it influence the situation at tau? Through this exponential attenuation. This is a formal solution of the equation which we've seen, allowing for the fact that you're traveling in some slant direction. Okay, so this is what I is back in terms of J. Okay, so now you integrate this I again to get J at tau. So you get this equation. J at tau is J at some other place times this kernel. And the kernel is obtained by integrating this over mu. So you've got rid of the angle variable. You've got an equation for the energy density. Okay, and it's an integral equation. And this kernel is E1, which is actually called an exponential integral. It's the integral of e raised to minus x over x taken between finite, maybe infinity on one side, but see, infinity is because as mu goes to 0, you can travel any distance. But there is a minimum, which is tau minus tau prime. Okay? So this exponential integral is weakly divergent when tau minus tau prime is 0. It's got logarithmic singularity. So this is exactly the kind of thing which would make people like Wiener and Hopf lick their lips. And so they developed a very nice theory of such integral equations, okay, which Chandrasekhar was fully familiar with. It's very elegant in its own right. Okay, so if this was the Wiener centenary, probably the rest of the talk would go into how they split this into functions analytic on one side of the half plane or the other half plane and so on. But there was a good astrophysical reason why this was not the place to stop. Okay. By the way, they were actually able to give almost exact solutions to this. The cases of interest actually have anisotropic scattering. So one of them, for example, is you have scattering from electrons, and if you don't worry about polarization for the moment, then the angular distribution is some 3/4 into 1 plus cos square theta or something like that. So it actually depends on mu squared. So this is one of the angular distributions which Chandrasekhar extensively studies in his book. So that sigma mu mu prime has this form. The other form which he studies is a simpler one which is linear in mu. So you have more scattering in the forward direction and one in the backward direction. He doesn't tell you why. I thought about it, and it's probably the appropriate one for neutrons, right? 1 plus x times mu. So, the neutron hits the moderator, and then I think in the center of mass frame it may be isotropic, but the whole thing is biased by this collision, and it's 1 plus x times mu. So in any case, this simplicity of just integrating this and replace, you have a sigma now sitting here. So this, you can still get integral equations, but now you will not have to work only with the energy density. You will get some coupled integral equations for some limited number of moments. Okay, so that's what happens. So Chandrasekhar does this, he says it, and then he says, no, this is not the way to go. Okay. So what is the way to go? And this is where there's a kind of surprise. because, today the thinking is that, the great minds solve things analytically and the lesser minds do things numerically, right? But Chandrasekhar has strangeness in his proportion, a phrase that he was very fond of. So then the book begins with a numerical scheme. He calls it the method of discrete ordinates, which even by the 1940s is a kind of nice archaic way of saying that the variable mu is divided into some discrete points. So instead of having, so I is no longer a function of a continuous variable. So instead of having just two L and R, you now maybe have some I1 to I2n or something, which are some 2n discrete directions which you have picked. So now instead of being an integral differential equation, you have coupled differential equations for some finite number of i's, which is the radiation in multiple streams, just like the streams I had in that figure, if you remember. Suppose the number of streams is really discrete, but not just two. Now this really looks like a cop-out, right? I mean, why would he want to do that? Okay. So, so then one of the nice things about Chandrasekhar's book is that in any book you have prerequisites, right? So he could very well tell you, as Halmos did, that the reader should not be disappointed if he does not have the prerequisites to read the prerequisites or something like that. But he actually gives you a nice lecture on. So, for example, in stellar structure, he gives you a lecture on thermodynamics, and incidentally, I think also solves for Dirac equation in a box. I think I should check that. And similarly, in this, he gives you a nice lecture on how to evaluate integrals numerically, Gaussian quadrature. A really beautiful chapter on that. Okay. And the idea of using Gaussian quadrature is actually not his. He acknowledges that he borrowed it from a paper by Wick. And this is again the Wick whom many people in math science would have heard of, the Wick of Wick's theorem and the Wick of Wick rotation and so on. So again, if one is thinking historically, why would Wick be sitting and working with a radiative transfer equation? But when I went to Wikipedia, sorry, no pun intended, turns out that he had a close association with Fermi, and my guess is that he was working on the neutron transfer problem. Yeah, absolutely. But I think moved to the US and so on. So now some miracles start to happen. So Chandrasekhar sets up these coupled differential equations, exactly like the equations for L and R which you saw, just more of them. But he chooses these points not equally spaced, but spaced according to the zeros of the Legendre polynomials, which is what Gauss did long ago and did for an extremely smart reason, that it cancels errors to order 2n. Whereas any naive discretization, like equal spacing and so on, would only cancel it to that order. Okay. So he gets a set of coupled equations. Now again, at this point, you could say, well, I have solved the problem. This is a set of linear equations with constant coefficients. I'm going to assume a solution of the type e to the k tau. I'm going to get a polynomial equation for k. I mean, just like we do it for constant coefficients, right? And, I'll get those roots and then fit the boundary conditions, okay? So this looks like an absolutely pedestrian exercise, the way that people would do it in the 21st century. You call the graduate student, give him these equations, he goes to Mathematica, and the whole thing is over in a week, okay? But this is where Chandrasekhar sort of decides to do things differently. So he has these equations, but because these mu i's are not just any old points, but they are the zeros of a Legendre polynomial, and these k's, in e to the minus k tau are again the roots of not just any old polynomial, but a polynomial whose coefficients come from this whole thing. He starts manufacturing some identities, okay? And as I said the previous time, 15 years ago, I was baffled at that point, but this time I went through it. It's extremely ingenious, and therefore he's actually able to make certain statements without actually solving for the roots and without solving for the so the kind of statements he can make are the following. So just to take you back to your days of black body radiation, you might remember there are two Stefan's constants, one which gives you the energy density and the other which gives you the flux emerging from a unit area, and they're related by a factor of c over 4. The 1/4 comes because things are emerging into a hemisphere, okay? Now of course here things are not emerging into a hemisphere, there is a law of darkening, okay? So what is that constant? Now people like Hopf had shown that that constant is exactly 1 over root 3, okay? F is j over root 3. Now the remarkable thing about Chandrasekhar's scheme is that even from the very first thing with just 2 points, where you might remember that the zeros of P2 are 1 over root 3 and minus 1 over root 3. He gets this relationship, what he calls the Hopf-Bronstein relationship. And because he gets it at every order of the scheme, it's an exact relationship. The second is this reflection problem. Okay, so now say you have a planetary atmosphere and the sun is not at zenith, it's at some odd angle. So there is a mu naught, the angle at which the rays come in, and then you want to know how they come out. So how are they distributed with mu? So there is an appropriately defined reflection coefficient, S of mu phi, mu naught, phi naught. And when he works this out, as I said, without firing a single shot, without actually solving for these roots or anything, he finds that this has a factorized form, which we will see presently. Okay. So at this stage of the work, he found that even though he started with a numerical scheme, he had exact results. Incidentally, that didn't prevent him from actually pushing the scheme to completion and drawing up elaborate tables of the darkening law and the reflection coefficient, etc., etc. That's all there in his book. But this is what intrigued the analytical part of his personality, right? And this is the point where even Chandrasekhar appears to have needed some help and some inspiration. Okay, what is the origin of these mysterious things? And he acknowledges it quite generously to Armenian astrophysicist by the name of Ambartsumian. Now, people in astrophysics know him very well. He's one of the giants of 20th century astrophysics. I mean, in some sense, you could call him the Chandrasekhar of Armenia. Okay, and again, I marvel at the fact that in 1940s, where I don't know whether the flow of journals from Armenia to the US was, Chandrasekhar actually read this paper, which is written, and he finds that Ambartsumian has come up with a beautiful idea, an idea which solves some of these mysteries which he has encountered in his numerical scheme. And I'd like to explain that idea to you. It's called the principle of invariance. Okay. And this is Ambartsumian's principle. So his point was that if you are, say, solving for the reflection from a semi-infinite slab, okay, and you have some S of mu, mu naught, or something like that. Imagine that you added a layer of thickness d tau. Okay. Now, on the one hand, it's still a semi-infinite slab. Okay. So you should get exactly the same answer. On the other hand, if you think of it as a perturbation of the original problem, then you get lots of terms. Like, here is the original scattering from the original slab, A, comes and goes out. Now, this is actually going to get reduced, because this is going to get attenuated by an amount proportional to d tau divided by mu, mu naught. This is going to get, so you will get a negative term with a 1 over mu and a 1 over mu naught. Okay? Then you will get a positive term, which is something which never reached the slab at all, but just bounced off, coming in at mu, going at mu naught. Okay? So, so that's why, let me show you the analytical formulation of this. So the negative term has been transferred to the other side, S of mu to 1 over mu plus 1 over mu naught, and right? So then, let's go back, look at all the terms of order d tau. Then you can have a situation where something comes in at mu naught, doesn't get attenuated because we've already taken care of that, comes out at some mu prime, and then gets diverted from mu prime to the final mu. That's a term of order d tau. So wherever you have this vertex, it's order of d tau. Then you have something which got diverted on the way in, but came out in the final direction. And finally, this is also a term of order d tau, if you think about it. There is an S, which now goes from mu naught to some mu prime, goes from mu prime to mu double prime, and then there's one more S, and that's it. These are all the terms of order tau. So you get this identity, which is derived by Ambartsumian. It's a powerful constraint on this S of mu, mu naught. Okay? And so these are the various terms that I described to you. Right? This is the direct scattering from the slab, and these are all the things that you have. Okay? So now, what Chandrasekhar does is to say, this factorizes actually, if you think about it. It's 1 plus this integral, I mean multiplied by a similar looking integral. Okay? So Chandrasekhar defines an H function, which is 1 plus this S. This 1 over mu prime occurs for the kinematic reasons I said. You traverse slabs at some angle. And then that identity now becomes S mu mu naught, etc. is simply fact. So when I told you the reflection coefficient factorizes, something which he had already realized based on a deep study of the numerical scheme, this is the form of factorization that he obtained. And now he says that mystery is solved. It's from this principle of invariance. So in fact, this is something I asked my particle physics friends. The one parallel I could think of is that, at least in my limited reading, you carry out something like a gauge transformation, small gauge transformation, which ought not to affect some amplitude, but in perturbation theory it does. You pick up all those terms and they all have to cancel. And these are some identities which are very useful in particle physics. But the remarkable thing here is that this identity, so now you do the same thing. You've got an expression for S in terms of H. You've got an expression for H in terms of S. So you plug that back in and you get this integral equation satisfied by H. Okay. So this was Chandrasekhar's take on, this is after absorbing from Armenia the principle of invariance, that now he did not have to go order by order, discretizing at 2 points, 4 points, 6 points. He could directly try and solve this differential equation, this integral equation. And to actually write down the solution and tabulate it, he went to the computer. Okay? I should tell you what computer meant in those days, but he went to it. Okay? But again, as in the previous instance, he was not satisfied just with computers. So one of the chapters in his book is called the H function. Okay? And it's entirely a study of functions which satisfy this integral equation. And it's amazing how many properties of it he squeezes out. Okay? But it doesn't stop there, because at this point he's sort of reproducing Wiener and Hopf, right? Isotropic scattering. And maybe some of you already feel this lecture has too many equations, but let me assure you that I'm sparing you a whole lot of other equations which are much longer than the ones that you have seen, because he was he was not doing this just for pleasure. He was interested in the finite slab because it's the planetary atmosphere. He was interested in anisotropic scattering, right? He was interested in polarized scattering. And in every case he found that some generalization of this framework worked. So every problem was reduced to either one, in the case of a finite slab, you had an x function and a y function which satisfied two coupled integral equations. And the beauty of these, again, I would say it's without firing a shot, because you never actually solve the underlying integral equation for I of mu. You just use this principle of invariance and you obtained it. Okay? And his point is, these equations look incredibly complex. But the point he makes is that because of this guiding principle, he actually knows how to write down solutions. The whole machinery which has been calibrated in this isotropic scattering case can now be unleashed on these more complicated problems. And it's all done there in the book. Okay? Now let me say a little bit about polarization. Now, one of the remarks that he makes is that, of course, you all know Rayleigh's 1871 paper on polarization and the color of the sky. But in some sense, it stopped there. Okay? And that was single scattering. So in single scattering, it's very, very simple. If the sun is somewhere over there, then I get direct radiation from the sun, which is unpolarized. But maybe something goes there and comes back to me. So take the extreme case of 90 degrees, right? So only the component which is polarized up will come to me. The component which is polarized horizontally will be longitudinal as far as I'm concerned. I'll get nothing. So that's the simple-minded, 12th standard explanation of the polarization of skylight. But actually, people who really looked at the sky through polarizers knew that this was not the whole story. So first of all, the light directly from the sun is not unpolarized. Okay? And the light at 90 degrees is some 89% polarized. It's not 100% polarized. And the actual points where the light is unpolarized are displaced from the sun. There are 4 of them. There are 2 around the sun and 2 around the antisolar point. Okay? So these were already studied in the 19th century, named after famous people like Brewster and Babinet and so on. And you can sense the irritation in Chandrasekhar's voice, where he says that these have never been properly explained. It's not for lack of trying. People had written papers on it, and he demolishes those papers because each one of them, say something qualitative or make some mistake and so on. So he says, look, we don't even these people are not even using the right variables to describe the polarized light. And now I come to, he lays a lot of importance on this, that he will describe it in terms of Stokes parameters. And today that seems a very strange thing, because all of us are educated that you should describe polarized light in terms of Stokes parameters. But, and I have no reason to doubt his word, that in the 1940s, apparently people had completely forgotten Stokes. I mean, of course, people knew density matrices, and the Stokes parameters are the density matrix of polarized light, but at least in the literature on this problem, people were struggling with various things, and they were not using Stokes parameters. So that's the first lesson he gives. And clearly he talked to some of his cousins also, because soon after that, people like Ramseshan and Ramchandran wrote this review on polarized light, gave due importance to Stokes parameters, and Pancharatnam, of course, did some very brilliant things on polarized light. Okay, but anyway, that may have been some direct transmission within the family, but in the community, it appears that he was one of the first to introduce this. So then he sets up the equations of transfer, and because there are 4 Stokes parameters, these are matrix equations. So your epsilon mu mu prime actually is a 4x4 matrix. And he repeatedly makes the point that it's because he understood the structure of the solution from these deep principles that he is able to wade through equations of stunning algebraic complexity. Okay? And then he actually compares to a remarkable experiment. So there's, I think, a Swedish scientist went to a remote island where there was no pollution, no nothing, and carefully measured the polarization of the sky. So he compares against that data set. Okay, and elaborate curves are drawn, and it all works out. And then, of course, he also develops it for planetary atmospheres, more generally. Okay, so that's the polarization part. Now, where am I? If I can read that clock correctly, I have about, how many minutes? Oh, okay, good. So then I can certainly tell you about something else. And I think this is important as a counterbalance to what I have just told you. Because on the one hand, you have very nitty-gritty problems, but you also have this touch of elegance, right? Now, here is something which also has inspiration, but an enormous amount of perspiration as well. And we have to appreciate that Chandrasekhar could do this. So this is Chandrasekhar as a quantum chemist, okay? And the background is that in the early days of quantum mechanics, the 30s, I mean, people, of course, did the hydrogen atom. They did a pretty decent approximate solution of the helium atom. And then the natural question was, what happens to 2 electrons bound to a proton? And there it turned out that if you do the same simple approximation that you do for helium, this is unbound. And the reason is that that approximation neglects the correlation between the 2 electrons. It just assumes the electrons are in both sitting in a 1s orbital, and then you overestimate the Coulomb repulsion, and the state is unbound. So professionals in the field like Hans Bethe and Egil Hilleras, whom wrote down very complicated correlated wave functions, and then did elaborate numerical computations, and they proved that it was bound. And since you're using the variational principle, it's enough to show that, if you get an energy which is going to be higher than true energy, and if that is negative, then you're fine. It's bound. Now, the relevance to astrophysics came when one of Chandrasekhar's colleagues in Chicago called Rupert Wilt had this inspiration. Apparently, there was a long-standing discrepancy simply in the spectrum of the sun. Okay, now sun to 0th approximation is a black body, but when you look at it very carefully, in the near infrared, there were some non-black body features, and it was not explainable by the standard models. And this person said maybe it's because these people are not putting in H minus. Okay, sort of interesting. We think of the sun as a place where electrons are stripped off, but this is a place where electron seems to be added to an atom which is very reluctant to take on that electron. Now, I still don't know why Chandrasekhar got into this problem, but he got into it. And the first thing he did was to produce a much simpler wave function than Bethe and Hilleras, but also one which gave a lower energy. So, if you're doing variational things, then that is the ultimate one-upmanship, right? That you've beaten the other person by doing less work, all right? But he didn't stop there. And then paper after paper, this was improved. The energy was computed, the oscillator strength was computed. I call it heroic numerical work, and I put the IN because the computers were actually 2 ladies called Frances Breen and Donna Elbert. And I think it varied. If you were a secretary to Chandrasekhar, you had to do many things. You had to look after the Astrophysical Journal, you had to And then you had to do this numerical work for him, which had to be on these facet machines. So these ladies actually cranked these things, but under his eagle eye, because he had a deep understanding of numerical analysis, which comes out in many of his books. Okay, so you have these papers by Chandrasekhar and Breen improving the thing. So let me just tell you what his inspiration was. I've told you about the perspiration. The inspiration was, I'm going to put the two electrons in two 1s orbitals with different radii. And that already is, I don't know what he was inspired by. It could have been the concept of a hierarchical binary in astrophysics, where you have a tight binary and one more guy going around. And that seems to be a very physical picture of this hydride ion. I call it the snowflake in hell. There's no right to be there. By the way, the reason why it is there is that there are these easily ionized elements, magnesium, calcium, and so on. And those electrons form a population which can drive the reverse reaction of producing H minus. Okay?
In this case,
yeah.
it could be a simple screen. One electron screens the proton. Less charge.
That's true. You're right, but that is lost if you put them both in 1s orbital of the same radius. No, that also has some screening, by the way. In helium, you get the 27 by 16, right? You might remember from your MSc days. But that's not good enough. So I would call this a broken symmetry Hartree-Fock equation. When you do Hartree-Fock, in this case, the symmetry would tell you to put both in the same orbital, but he put them in different. But it's also, then he anti-symmetrizes, he symmetrizes, of course, because they have opposite spins. But as I said, again, there's the inspiration, but he's not a hit and run kind of person. So then for another 5 years, every T is crossed and so on. Okay. So now let me come to the broader picture, because the idea was to appreciate, look at it in terms of style. And there are questions one can ask. After all, he had the Wiener-Hopf equation. There was already an integral equation. At the end of a lot of effort, he has another integral equation. That was linear, this is nonlinear. Okay? And on the one hand, there is all this elegance, all this beauty. There's also enormous hard numerical work. Okay? And in some sense, as I told you in the beginning, it's a mundane problem. As I said, people like Eddington had produced a fast solution which might have been good at the 10% level and then carried on. But so these are all aspects of his personality. And one is left guessing as to why he was so happy with this. And I suspect it must have been these eureka moments. And there are at least two eureka moments here. One is when this numerical scheme started giving analytical results. Okay? And the second is when he read these papers by Amartya and suddenly he realized that they opened up a whole range of problems to this approach. But its characteristic of his personality is that he did not shirk all the hard numerical work and so on, which went to following these up absolutely to the logical conclusion, as far as he could go with this thing. And of course, he himself has written about this. He's been quite generous in his acknowledgement of Amartya. So what he in 1980, which is well after all these events, he visited Armenia. And as he said, it's the second time he met this gentleman. The earlier time was 1935. Is the time that he met Landau, for example. It's not little known that they met. And he also met Amartya, and he generously acknowledges the inspiration. But again, another aspect comes out while reading this book. Chandrasekhar is competitive. Right? He takes a lot of pleasure in taking a problem which someone has either solved by a more difficult method or not quite got the solution, and he tells you that this is the way it should be done, and you do it. Okay, so that aspect of his personality also comes out, and particularly in the polarization part, where it's almost as if he didn't like this mess which was going on, and like a good householder, he cleaned it up, so that it satisfied him. Okay, so anyway, this is my kind of reading, and you also find out that it's not that he didn't read the literature. Apart from editing the journal and writing an enormous number of papers, he doesn't seem to have missed a single paper. Even if it was in German or a long time back. Oh, sorry, I'm going the wrong way. So these are my conclusions, and perhaps his remark on it being the happiest period is that amongst his different works, this seems to have been the one. He later in his life, where he let his hair down and talked about the novels of Virginia Woolf or the paintings of Claude Monet, and he talks of different parts fitting into a whole, but the whole also having some strangeness. And I think the book on radiative transfer and presumably the work satisfied all these aesthetic criteria which he had. And as I said, if one is sort of matlabi and really wants to get into radiative transfer, you can learn a few equations, and at some point you have to go to a computer code. So in some sense, everything he did has been bypassed. Not the mathematics. The mathematics was taken up by people in other fields, the integral equations and so on. But today, radiative transfer would not be done this way, but it's still worth appreciating that this phase of his life and this particular style of working. Appreciating doesn't necessarily mean emulating, but this is the exercise that I have gone through, and thank you very much.
Any questions, comments?
Yeah.
Let me first make a question, and then I want to make some remarks. First is that equation you wrote for H.
Yeah.
That looks like a problem in analytic functions, no?
Yes, I didn't tell you, but he takes off into the complex plane at that point.
There is this Hilbert transform. It looks like a Hilbert transform of sorts.
Yeah, it's one-sided though. All the mu's go from 0 to 1.
But
Huh?
okay.
So that is, it's not quite, you can't close the contours completely,
It's
but yes.
invertible by, I think, by known methods. Maybe.
No. So he does. I don't want to say that
Okay.
he derives many analytic properties of this equation
Okay.
by going to the complex plane.
Okay. Second question is, second remark is, this is a general remark since you're, is that it seems to me, also from my interactions with him, that Chandrasekhar was a very conservative physicist. For example, all the work you have described are classical. Okay?
Yes.
Even in the mathematics is 19th century mathematics. I don't see anything on global properties of PDEs or anything like that. Okay? Or very innovative work like that of Dirac or Heisenberg or
Agreed. Agreed. His tastes are very classical. I would agree with you.
Furthermore, I do remember his telling us, asked me, I, Rajaji and Ramachandran, who is not here, once, that he had no idea why gravity should be quantized. At that time, we were very young and we were surprised.
Which year? See, he started getting deeper and deeper into gravity
Yes.
much later than the period you are talking about.
No. I was there. I attended his course.
Okay.
The first course where he will bring what book? Landolicious. Then he will go through equation by equation, working
Right.
it out on the blackboard. Okay? And secondly, I also remember he's telling me that when Ed remarked somewhere that string theory is the physics of 21st century, he was deeply offended. Okay? He told me this much. Okay? So he's, in my judgment, he's a very remarkably capable classical analysis type person. Even quantum mechanics is quantum mechanics. There is nothing quantum field theory here. But on the other hand, he was somehow very conservative.
See, one of the points I wanted to make is his dedication to the astrophysics. So even though he loved his tools, he was not purely devoted to the tools. I do want to make the point that he spent enormous time in ultimately delivering finished products to the Astrophysical Journal, maybe to himself, but anyway.
Yeah, this is about the quantizing gravity. I think Chandrasekhar was echoing what Rosenfeld.
Okay.
Leon Rosenfeld, collaborator of Niels Bohr, he had held a point of view for long years that gravity, there's no need to contest gravity. So he probably communicated the question to him, and this fellow, I don't know what they said.
But it's interesting because Bohr and Rosenfeld were the people who gave the simplest argument for why the electromagnetic field should be quantized, that you will otherwise end up violating the uncertainty relationship for an electron. So, right. I'm very surprised because he's the one who gave the same reason for, anyway. Right. By the way, Chandrasekhar, he does record that when he was getting pretty sick of Cambridge, he spent a couple of months traveling in Europe. That's when he met Ambert Sumian and Landau and also spent time in the Bohr school, so certainly possible.
Rajaram, you mentioned about this helium.
No, H minus.
H minus problem. Sorry, hydrogen. So there you mentioned about Chandrasekhar's important separating the two orders.
Yes.
Because
So those were
that
the
became-
follow-up.
That
Yeah.
became in
Yeah. No, so
nuclear
but
physics
that
and-
was not original to him. That,
I see, it's
you're
not
right. The 1 over R, the R12 part came from, I mean, many
Miller
people did it.
assumption. I see.
Of course, I think there's also there was a cleverness in that because that would cancel the R12 in the Coulomb and so on. But anyway, yeah.
There is something called invariant embedding method. Is it
That
the
is
same
this
as
principle of invariance. That's so. It's true that this was very classical mathematics, but it was taken up by people like Bellman, Tom Kailath, and so on, applied to problems which are mathematically similar, though the physics is very different. But that's applied mathematics, right? So, with regard to pure mathematics, I would agree with you, except that I suspect what I hear in the context of relativity is that he tried to teach himself all this modern stuff, but since he knew that that was not his style, he digested it, but just kept it. I mean, he didn't practice it.
So, Rajaram, there is one polarization problem of importance in astrophysics,
Yeah.
which is a scattering atmosphere, semi-infinite medium,
Yes.
radiating from below, and then the radiation comes out.
Yeah.
And you want to know how polarization varies with angle from the normal.
Right.
And there is a famous Chandrasekhar formula for this thing. What I was interested in is how closely are those results mapped onto the Rayleigh problem? The 11% deficit that you talk about in the
No,
Rayleigh
the 11% refers to exactly his famous solution.
His famous, so it is
Solution,
that
right.
solution?
11%. It refers to, I called it the 11% solution.
Okay.
Huh,
And
that-
so it is the same solution for this
It's exactly that problem.
semi-infinite medium as well?
Yes, it's that solution, the semi-infinite medium,
I see, okay.
which I think people have looked for in, yeah, it is exactly that problem. Of course, again, I do want to make this point that, and this I learned from an astrophysicist called Greg Shields. Suppose Chandrasekhar had not given this solution, you take the radiation field of the Eddington approximation and do the last scattering with Rayleigh, you will get very close to this. So, I mean, it's also the elegance, I guess. Yeah.
I must take exception to Bal's remarks about Chandrasekhar. Because I have limited knowledge of his work and so on. I never spoke to him. But starting with the paper that I first learned about Brownian motion and so on, never retracted anything. He was very proud of whatever he wrote and made no mistakes in everything out here. He never retracted anything. Okay, he didn't recant and so on. No? So that also, I think when he set himself a problem, he was went the whole way. No, even with the white dwarf limit and so on. 3 years or 4 years of working on the problem, looking at all aspects of things here, finding all ways of looking at the things and so on. That single-minded determination to solve a problem. That's something, the hallmark of his man.
Right.
I think that should be emphasized, not saying that he didn't know topology or didn't know different geometry and so on. I mean, that everybody is, in their understanding.
No, it shines through when you read this book. I mean, as I said, I have spared you the longest equations in this book. They're not the ones I showed you.
Can I ask a question?
Yeah.
This problem with addition, what you are doing was
Yeah.
addition. I thought that subsequently these formulae, this results have been considerably improved by semi-classical methods. This Kutzwiller trace formula, I mean, not for at least for the
Okay.
helium problem, I have seen answers which
Okay,
are much
okay.
more accurate than variational calculations.
I would.
This Kutzwiller trace formula, Zellberg trace formula, things of this kind. Am I not right? They have claimed that they get fantastic accuracy.
Okay. See, this has only one bound state, incidentally, and it has a continuum.
I understand.
And in fact, he was interested in not just getting the binding energy, but the entire absorption spectrum. So he
That is different.
actually did oscillator strengths to the continuum.
I understand.
Now, whether trace formula would give that, I'll have to think.
That I do not know.
I'm a bit
But
rusty,
in
yeah.
any
But I
case,
can certainly follow that up because I do have good friends who do a lot of quantum chemistry, so I will ask them.
They should know.
For example, density functional, will it give you a bound state for H minus? I mean, I'm going to ask Shobhana Narasimhan the next time I meet her. It does not? Oh, you know that, huh? Apparently, it doesn't give a bad result even for H. I mean, it's ridiculous, right? You have a theory of n electrons and you apply it to 1 electron. Apparently, it doesn't give a bad result, actually.
because of this correlation. This says
No, no, but
electrons avoiding each other. That is not captured by this.
then, of course it is. Of course it is, Bhaskaran. No, it does. Okay, we should talk about it. I thought it is. Huh?
In fact, the whole thing came in the context of some hydride.
Okay.
This atom.
No, I would like to learn that from you, right?
Anybody else want to ask questions? Okay, we'll thank Professor Rajaram.